So if we think of them, your particles need to collide in order to proceed from reactants to products. They need to have sufficient energy. After they find each other, they need to have the energy to go ahead and make a successful collision. And sometimes, not only do they need to collide with the sufficient energy, but there's an orientation factor. So they need to be properly oriented. And I'm going to show you a little video of each one of these. Okay. So we're going to talk a lot about reaction rates. How fast does a reaction occur? And we're going to actually see the influence of the concentration of the reactants. We're going to see the influence of temperature, and actually the concentration of the reactants on the reaction rate is a little more, you got to chase it around. Temperature, by golly, if you increase temperature, that thing's going to go faster. That's nice. Surface area, I have a video later to kind of tell you, but basically if you make more surface area, you have more possibility for them to collide. So reaction rate goes up. A catalyst, reaction rate goes up. So actually those last three, if you increase temperature, if you increase surface area, if you add a catalyst, if the reaction has the ability for a catalyst, then your rates are going to go up. Concentration of reactants, it's a little mixed bag. It doesn't always go up. I know it seems like it should always go up. So this is a little bit getting ahead of myself. Here in the next, I don't know, 10, 15 minutes, I'll be talking about something called what the reaction order is. I'll go ahead just for kicks, I'm going to put the variable M and N. Those are like little variables we're going to talk about reaction orders. If the reaction order is positive, which most of them are, then we're going to see actually, yeah, if you add more reactants, the rate's going to go up. Okay, if they're negative, not so much. Actually, just the opposite. Increased temperature, reaction rates go faster. And it's kind of like one of the variables we saw just a minute ago was sufficient energy. So if you increase the temperature, basically your solution has more energy to proceed from reactants to products. That's why it goes faster. Surface area, increased surface area, rates go up. Catalysts. Now, in biology, seems like there's a lot of catalysts for things that are chemistry that's going on in our bodies. The thing about a catalyst is it's an optional thing, so you won't see it in a chemical reaction. You'll see it usually over the reaction arrow or the reaction chemical equilibrium sign. The other thing about catalysts is they're like the burning bush. They are not consumed. So catalysts can be used and reused till the cows come home. Okay, so it does not go away. But it always makes it go faster. So let's take a look at these. Okay, so this whole how fast will a reaction rate occur? Reaction rates. We've just been kind of talking about, well, most recently, just kind of generally speaking. We need to kind of get into specifics with regard to something mathematical. I guess that's my point. Mathematics. I am in wonder sometimes about kind of this basic chemistry. This is still just basic chemistry. How fast does a reaction occur? How they came up with how this works. But the rates, we're going to talk about kind of the mechanism associated with the reaction later, kind of the steps going on behind. But that's just the observable reaction rate. So there are going to be some mathematical expression. And you're going to see me kind of call it a rate law expression. That's just your math, basically, of saying how fast your reaction rate is going to go. And here on the left, you'll see rate. When I say rate, it's reaction rate, okay? And then the whole thing is your rate law expression. It could be also called the rate law equation, rate law, but it's all the same thing. It's going to be rate is equal to blah, 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 blah. Okay? So we do a lot of this kind of just generic. I'm going to take two things. A reacts with B to go to form products. Okay, this is my generic sort of situation. Okay, it's a one-way arrow. We want to kind of talk about how fast that occurs. We come up with our rate law expression. Our rate law expression, and I think I'm going to go ahead and put this on the board so I can kind of mirror it. This is the generic one. You're like, what the heck? Remember I said a little bit ago, reaction orders, M and N? Here's your M and N. Okay, so if we simply have A, small a is the coefficient of A. Small b is the coefficient of B. Go to form products. Our rate law expression, reaction rate, how do you want to say reaction rate, same thing, is equal to K. And remember, anytime you have something in brackets, that's the molar concentration. The molar concentration of A, the molar concentration of B, each one of these are raised to their own reaction orders. This is their reaction order. Okay, that is their own personal reaction order. Okay. Now, if we're talking about, remember we said reaction rates, the problem is, like, a reaction rate's slow over time, because we kind of looked at that on Wednesday. So there's some times when we'll kind of be focusing on the initial reaction rate, the fastest. And your initial reaction rate will be equal to the molar concentration initially of A, reaction order, initially of B, molar concentration of its reaction order. Another K. Remember I told you? I'm like, oh no. Can you not come up with another variable? So K, actually, we'll be calculating some Ks. And honestly, back Wednesday, do you remember we looked at one data of reactant goes to form products, and at the bottom it said K is equal to? Didn't know what that was, but actually that's the constant K for that data that we looked at on Wednesday. You're going to be coming up with your own Ks. K depends upon temperature, and it depends upon the reaction that's occurring. So in this case, initial rate, initial, I could go ahead and put little, remember this is the initial molar concentration of A, initial molar concentration of B. And again, those M and N's, now you can't leave them as M and N's. You actually have to put real numbers there. You can, but we gotta put real numbers there. I will tell you, let's see, how does this work? I could underline each one of them. And each one of these, you get, well, maybe not that one, or maybe. Each one of these, you get by observation, okay? So experimental data. Basically, you run this reaction, you evaluate it, and you can come up with these things, okay? You too can come up with your rate law expression. So this is kind of the bare bones generic one. Okay, so do you guys buy this? This little superscript, these superscripts M and N, these are actually the power. Like you take the molar concentration of A, raised to that power. Molar concentration of B, raised to that power. How does it affect your initial rate? You'd be like, I don't know, but I'm going to tell you, if you look at data, you can know. Okay, now the fact that this is in red and the next one is blue means that is very, 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 very important. Do not simply take the stoichiometric coefficients, for instance, of A, do not make it your reaction order B. No, 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 no. Do not take the stoichiometric coefficient of B and make it reaction N, reaction order of B. Do not do that. Clear at the end of Unit 1, I'm going to tell you in the very, very specific case, and I'm lowering my voice, in a very, very specific case when you can take the stoichiometric coefficients and make them the reaction order, only if they are what we call elementary steps. Okay, so the only way in B, like I said, the only way you get to the reaction orders is by experimental data. And we're going to do an example. Okay. All right. So one last thing before we do our example, or actually a few more things, I can remember this. There's something called the overall, so there's the reaction order for A, the reaction order for B, or M and N, and then the overall is you just add them together. If you had a third term up there, if you had a reaction order of C, You just add them all together and you get something called the overall reaction order. So in this case, your overall reaction order is M plus N. And I'm going to try to tell you why it is important to know the overall reaction order. Okay, so the overall reaction order, you just add them together. Okay. So reaction orders can be positive or negative. If they are positive, which the only ones we're going to look at, are going to be positive. We don't look at any negative ones. But do you buy this? If this was negative, if this was negative and you increase the molar concentration of it, then actually increase the molar concentration is going to decrease the reaction rate. We don't do those, but they can happen out there. Let's see. They don't have to be whole numbers. You're like, dude, really? It's true. So kind of near the end of Unit 2, we're going to talk about how you can have fractional reaction orders. If these reaction orders are greater than 1, if they're positive, or if they're 0, do you guys remember anything brought to the 0th power is 1. Okay, anything raised to the 0th power is 1. And if it's positive, then as you increase the molar concentration of your reactant, then you'll increase your rate. So we're going to spend our most time talking about reaction orders of 0, 1, and 2. Nice whole positive numbers. So reaction order of 1 is called first order. Reaction order of 2 is called second order. Reaction of 0 is called 0 order. All right. So we've talked a lot in Chem 1 about units, and you guys are doing great with your units. So let's start with this. The units on your homework that we talked about on Wednesday. Rates are always going to be, or most likely going to be, change in concentration per time. For instance, good units of rates would be moles per liter, molarity per second. That's a grade. Okay? Or moles per liter second. Same thing. So here's the deal. However powers these are raised to, the way I think of it, is your K, that is your rate law expression constant. The units of K kind of have to fix it so that you end up with rate moles per liter per second, or change in concentration per time. So here's the deal, and actually if you put a star up to this next one, this can actually kind of help. If you're given K, you can use the units of K that you were given to kind of backtrack as to what the reaction orders are. So for instance, okay, if your overall reaction order, that's M plus N, if M plus N is equal to 0, okay, means we have a 0 here and a 0 here, so basically our units go away, then K has to be moles per liter, or molarity per time. It has to be that. That works. If your overall reaction order, that's M plus N, is first order, then basically what you have introduced here, the way I think that what you have introduced here with first order overall, is 1 moles per liter. One molar, 1 moles per liter. So here's the deal. All you need K to be is per second. Why? Because you already have one of these terms. Okay, so if you're carrying already a molarity and you need molarity per second, all K has to be per second. If it's overall, m plus n is equal to 2, okay, then what you have done is basically introduced a moles per liter of molarity squared. Moles per liter squared. Okay, so in that case, you need to basically get rid of one of your moles per liter, okay, because you only want moles per liter per time. Still keep your per time. So basically you have to put one in the bottom, if that makes sense. To cancel this out, you have to introduce in your K not only time, but you also have to introduce molarity in the denominator. Get rid of one of your.
So is the units of K then, is it going to be different for every order?
Yes.
It just depends on what needs to be canceled out?
Yes. Yep. K's, this is a, I'll say unfortunate, but this is the reality of rate law expressions, is your K's units are going to vary with what your overall reaction order is, exactly. Yep. So this one, how do we express that? Well, since we have molarity in the denominator, we have 1 over time, and that molarity is moles per liter. We kind of think of it as flipping it up. That's why what you see is liters per mole. Or else 1 over time, also molarity down here. Okay. That's why it says liters over moles. That's basically the inverse of molarity. Yep. So this is an important slide. This slide, I think, says similar information. So if it's overall reaction order 0, again, then there's nothing to fix, per se. You have no units being introduced by your concentrations of your reactants. And so the units of K will be what the units of rate are, moles per liter per time. Overall first order, okay? Overall first order means that you're introducing one something raised to the first power, basically. Okay, and so then that's molarity. So then all you have to introduce with your K is per time, and you have molarity per time for rate. And last but not least, my favorite, is that if it's overall second order, then you basically have to undo one of your molarities that you've introduced, in addition to introducing time. So this right here is the inverse of molarity. Moles per liter. So those can be very helpful. Those two slides kind of go together. So let's look at some data. This slide actually is setting up the data you're going to see on the next slide. So let's just say that we run the experiment twice. This is kind of what we do. Okay. We're going to run it first at 0.2 molar for A, the reactant A, and then we're going to double it, and we're going to run it at 0.4 moles per liter. And you kind of see the generic equation we're working with down here. This is assuming that you have A is reacting with B to go to form products. So I'm going to try to kind of convince you that with the data on the next page, you can actually get that from data. You can get that from analysis of data. Okay, so we're going to run it twice. We're going to double the concentration for the second one. Oh yeah. And what you're going to see, the data on the next page is assuming, and this is what we do a lot of times in the lab, we are going to hold the molar concentration of B constant. And we're going to vary A. We're going to hold B constant. Now the cool thing about holding B constant, that's not an accident. Basically, if we hold B constant, then any changes in A is what's going to, or we're going to see a rate change, probably. So any changes we see in the rate, it's not due to B, because that's constant. It's not due to K, because that's constant. It's due to the change in the molar concentration of A. All right, so here we go. So up there at the top, you see kind of something called, I don't think we've talked about this before. You see the prime, the K prime? Okay, actually that is now what we call the pseudo constant. pseudo, I might have misspelled that, constant. Okay, the pseudo constant here basically, remember we said that B is constant? I say it's a pseudo constant because basically A prime, and sometimes we do this, A prime is actually, sorry, K prime. K prime is actually the old K, the rate law constant, times the molar concentration of B raised to its reaction order, because that's all constant. So we're just absorbing it. Okay, now with all that in mind, here's some data. All right. So this is your trial 1, and this is your trial 2. Trial 1, trial 2. Now, if your reaction order is 0, then we're going to raise the molar concentration up to reaction order 0. Molar concentration 0.4 up to 0. But like I said, anything raised to the 0th power is 1. So what we would actually observe running this twice, now these are, I'm going to show you some other examples. These are all different reactions because you can't have the same reaction in different reaction orders. So we're mixing up, we're taking different reactions. In this case, for this particular reaction, okay, we actually would not see an increase in our rate. Our rate would hold steady. Okay, reaction order 0. Okay, let's take it up a notch. Now remember we said that reaction orders don't have to be whole numbers. Let's go with 0.5. Reaction order of 0.5. So here we ran it once with the molar concentration of 0.2 to the 0.5 power. We get 0.45. We do that on calculators. If we double the concentration from 0.2 and make it 0.4, again raise it to our what we know, let's just say we figured it out, that the reaction order is 0.5, we get 0.63. In this case, it does go faster. Notice we don't have to worry about the pseudo-constant K prime because it's constant. So all we can get to do is worry about the molar concentration of the reactant that we are changing. In this case, actually, we could divide and actually have homework like this. If you, on your calculators, take 0.63, and if you divide it by 0.45, you get 1.4. That's where that came from. Okay, how much faster is it? 1.4 times faster. Well, let's continue this. Reaction order, first reaction order. Okay, so here we go. This was our original concentration, 0.2. This is our double concentration, 0.4. We're going to go ahead and raise it to the first power, which then we just get them back again. But if we take 0.4 divided by 0.2, you get 2. You get 2 if you divide 0.4 by 0.2. And last but not least, they ran a different chemical reaction, okay? And so it have a different reaction order of 2. So if we take 0.2 squared, we get 0.04. If we take 0.4 squared, we get 0.16. If you divide 0.16 by 0.040, you get 4. That's why it says your rate will quadruple, a factor of 4. That's what factor 4, quadrupling. Cool. So what I'd like most to, if you want to, focus on 0 order, first order, second order. So what you're looking at is if you double the concentration, just like we did here with A, you would say the rate stayed the same, the rate doubled, or the rate quadrupled, respectively. That's because we're focusing on 0, 1, and 2. Cool. Well, if you buy that, then that all works. Okay. So again, it's a little weird because, yeah, we were looking at A reacting with B to go to form products. These were all, they had to be different, reactions because they had different reaction orders. But to find the reaction orders, we're going to do an example here. If you have a set of data where you strategically change your molar concentrations and you observe how it affected the rate, you can actually deduce what the reaction orders are oftentimes. Okay, so, but like I said, strategic. So, for instance, in this example, even though B was involved, B was another reaction, we held B constant on purpose because we knew we wanted to just focus on the reaction order of A. We don't know what the reaction order of B is because we didn't change it, okay? So you strategically design your experiment, you grab your initial rates, okay, and you compare how your initial rates are affected by changing your concentration.
Write it later.
Okay. Now I'm going to show you by inspection. This first example is going to be by inspection. And then later on we're going to get to reaction orders from data using algebra. And then we're going to use another graphical method, Logger Pro. So this is the example we're going to look at. Now it does get a little, It does get a little hairy because notice we don't just have an A and a B, we also have a C, okay? So right off the bat, what I tell students is we could come up with just a generic rate law expression and it would look like this. I'll do it at the bottom here. We could say the rate or reaction rate, is equal to the rate law constant K times the molar concentration of the H2O2 raised to its reaction order, M, molar concentration of I minus raised to its reaction order, N, molar concentration of H plus raised to its reaction, LMNO. Okay? So when we look at the data here in a minute, we are actually going to be able to understand what this reactions orders are. But I like to do this when I'm working a problem because then I know what my target is. Okay, so we can get to each of these by experimental, the data. And actually, and it's really not too hard, I'm going to show you how we can knock out a K too. All right, let's see what this looks like. So on the next, and I printed it off and left it on my desk again. I do that a lot. You're going to see a series of, they're like 4 different experiments, okay, and the strategically, the amounts of the molar concentration of the reactants and were changed, and we looked at what the rate was. Okay, so I'll just put all these up here. So your next slide says what you do is you kind of put on blinders, and you focus on one at a time. So I bet you guys buy this. Do you see where if I compare 1 and 2, notice that I have held these, I've held my I minus and my HI constant. So anything I see over here is due specifically to the molar concentration of my H2O2. And just eyeballing that, looks like it doubled, doesn't it? Oh, so a few slides ago we said doubling was first order. Bada boom, we know what M is. Okay, we're going to do kind of similar things for, let's see. What do you think? If we compared the first and the third, okay, in that case, it looks like, you know, your H2O2 is constant, your H plus is constant, okay, and notice actually it doubled too. So I'm getting the reaction order of I minus is also 1. And last but not least, I'll change to purple. Looks like we must be using this last row, so if we do it looks like, oh yeah, what if we did 1 and 4? Okay, notice that their H2O2 was held constant. Your I minus was also held constant. And the only thing that was changing was your H plus. But now we have something interesting here. Notice that it's the same. So what reaction order is it? There's no effect.
0.
It is 0, right off the bat. So we can actually kind of go across the board and fill those in. So I don't know, speaking of fill in, I'm not sure what you need to fill in here. Determine the reaction order for a reactant. You find 2 experiments like we did a minute ago, and where the only difference is 1 reactant. Okay? So if we compare experiments 1 and 2, we can focus on the effect of the H2O2 because the other was held constant. We notice that the rates for 1 and 2 was doubled, so that makes it first order for H2O2. That's M. And when we compare, again, experiments 1 and 3, the thing that changes is your I minus. The H2O2 and the H plus are held constant. And again, we saw a doubling. So that must mean that it's also first order. And then last but not least, we compared 1 and 4 to get a fix on what the effect of changing the molar concentration of H plus is. And we noticed it had no effect. So it must be 0 order. So now we're ready to go back to kind of the generic, and we're ready to plug some numbers in, which is kind of fun. So plugging some numbers into the generic rate law expression, now we can have H2O2 raised to the first power, I minus also raised to the first power, H plus raised to the 0th power. So actually, here in a minute, we're going to take that term and we're just going to, it won't show up in your rate law expression. I know we're pushing for time, but I do want to show you this one last neat little trick. So we're almost done. And sometimes on a test, this is how far I want you to get it, how far I want you to get it done. But we can actually come up with a K. We can come up with a value for K by going back to any of those 4 and plugging in these 3 quantities and solving for K. But if I'm thinking of this right, you're going to need to use what we talked about before when we said, what will the units of K be? So the overall reaction order is 1 plus 1. The overall reaction order is 2. So you know that units of K are going to have to be what? Liters per mole time. Okay. I don't know if it'll come out that way. Maybe it'll come out that way anyway. I think it will. Okay, so if we go back to our rate law expression, solving for K, K is equal to the rate or the initial rate divided by the molar concentration of hydrogen peroxide, H2O2, also in the denominator, the molar concentration of I minus. They're both reaction order 1. That's why there's an implied 1 there. And a lot of times I'll pick experiment 1 just because, but I think you should come up with the same K for all of your experiments. If you go back and pick experiment 1, going across, you'll see the last number was 1.15 times 10 to the negative 6 moles per liter per second. That's the rate. You'll see the molar concentration of your H2O2 is 0.01 molar. That's also the molar concentration of your I minus. So notice, though, that actually we do get the units that we said we should get. The moles per liter in the numerator cancels with one of the moles per liter in the denominator, and you end up with moles per liter in the denominator, which is the same thing as liters per mole. So we actually have a value for K. Okay. So this one, and I appreciate your patience. This one is going to be due on Wednesday. I'll take a quick look at it. And I'll push it out there. 14.1. We're in chapter 14, finally. Here it is. All right. So looks kind of similar. A reacting with B to co-form C and D. And notice that they, now these aren't as obvious. You're going to have to do some kind of dividing on your calculator because otherwise it's not obvious what's doubling, what's tripling, that sort of thing. But you should be able to apply the exact same thing we did a minute ago. My hints were, well, my hints. This is one from last year. To find M and N, reaction order of A and B respectively, basically choose a pair where only one of your concentration was changing, and then compare what happened to the rate. And like in the case of experiment 1 and 2, you know it's the influence of B, so you can actually come up with a reaction order for B by noticing the observed change. And if you're like me, you have to take 1.35 times 10 negative third divided by 3.35 times 10 negative fourth, and then see what it is. So you need to knock out both A and B, M and N, and then the overall reaction order, that's just adding them together. And then the value for K is kind of pick any experiment and plug in your molar concentrations and your rate to get K. Okay? Thank you. That's it.